deployed RDMA hardware that we use in the supercomputers, just in case if you want to couple it with the hardware. So let's talk about some experiments. So we have done some early experiments between two IBM FX22 blades, which has dual quad-core Intel Xeon processors. They have 8 GB of RAM, and they are connected using 10 GB of Mellanox connectors adapter. And we have written our own RDMA test suite for the NetPerf application, which will be available soon. And these numbers which I'm going to report, they are average of three runs lasting a minute each. And for the TCP performance, for the baseline comparison, we actually report 2 variants of TCP. One with TCP receive copy offload, one without. And we'll see how does that affect the performance of the TCP. So bandwidth. So on the y-axis here, you have bandwidth in megabits per second. On the x-axis, you have buffer size. So it's just a simple TCP send receive kind of thing, right? So for the RDMA write, which essentially is writing the remote memory, and RDMA read is essentially reading from the remote memory and back to your own local buffer. You can see that with our implementation, beyond 16 KB for the write and 64 KB for the read, it doesn't impose any performance penalty. It's almost equivalent. Latency. So here on the y-axis there, you have latencies in milliseconds, and here you have a receive side CPU usage to support to process the networking traffic. So you can see that we are able to support lower and better latencies than TCP, and that's good, right? And then we started to dig a little bit deeper exactly what is the root cause of this gain, and we found out this is because of the TCP receive copy offload. So as you can see, the TCP has a better CPU usage than us, but at the same time, it hits the performance. So if we disable the TCP receive copy offload, and then the performance gap kind of closes. So we still are doing slightly better here, but it's hard to show in this graph. But to actually achieve the similar performance from the TCP point of view, they have a higher CPU usage. So the gap, so they have to use like 20% more CPU to actually support the similar performance. And this is for the, yes. And this lower CPU utilization actually results in better CPU efficiency in terms of receiving the networking traffic. So in this graph, on the y-axis, you have gigabit received per second using gigabits received, gigabit per second received using per gigahertz of the CPU. And this is the message buffer size. So as you can see, TCP able to manage for around 4 gigabit per second using 1 gigahertz of the CPU. And after modestly large buffer sizes, we managed to pull around 5.3 gigabit per second from the same setup and same stack. So in conclusion, network I/O didn't change in the last 3 decades, but a lot of things has changed. Hardware, performance requirements from the application, and things how we use them. So it is kind of time to actually reevaluate the networking stack, considering the changes, what's going to happen in future. And the applications which actually do lots of network I/O, they deserve a better support from the OS to do these kind of things. And we can learn a thing or two from the supercomputers, and gains are even possible considering the principle and software that they have developed from the supercomputer if you apply them intelligently in the commodity clouds. And as an illustration of our argument, we have implemented RDMA stack in pure software without modifying the vanilla kernel. It's an open source project. The code is available here. You can go and check it out. And that's all from my side. Thanks a lot.
So in fact,
how do you handle the cache coherency problem? If you do RDMA, you have to the cache.
Actually, it's RDMA is not to support this distributed virtual memory kind of thing. It's not. you can use it, but in this work, this is not what we are trying to do. So it's just, right?
I'm not talking about just to show the memory. I'm talking about the cache memory processing.
Yeah.
Actually, physical memory. So both they are.
So, but it's the same problem in the next one. Yeah.
If you DMA,
yeah.
that's taken care of by DMA hardware. In your case, you're doing software. So
no, we are
to make sure the cache and memory.
No, okay. So in this work, we are not doing DMA. So it's like we are doing things semantically different, but in the end of the day, the DMA is done by that commodity name. So it's the same problem how you handle. So the buffer that we are going to transfer and receive, it is marked as DMA code. So it's not cacheable, and operating system generally just take care of that in terms of synchronizing the cache. Well, we can discuss in more detail for us.
So the main setting point is low latency, but I actually don't see that. So we can see the main setting point is low latency, right? But I don't actually see that. I see the gate is very small. So what is the latency achievable with a hardware gate? That will give us the baseline, right?
Yeah.
The software looks just it's a wash.
Okay, so with the normal Ethernet setting, they said that you should be able to get latency around 14 to 15 microseconds with our setup. If you do a ping, that gives us 30 microseconds, considering all the overhead. And so in this, I think in this slides, what we have shown, like this is, so in this case, so this goes, if you use even larger buffers in terms of like megabytes and gigabytes, this gap increases significantly. I can show you actually the backup slide, if you like. And so it's a kind of trade-off. So it's, at this point, using TCP copy offload, they managed to able to save CPU, but it hit the performance of the latency, right? So it's a kind of trade-off. So if you switch it off, then the latency gap closes, but it's still getting slightly better, which is hard to show. But they are using like 30% more CPU.
Yeah. So this additional software stack have to maintain to get this kind of gain. Because to me, additional maintenance you need to put to maintain this new software stack. Comparing with this performance gain, to me, it's like not significant.
Well, yeah, okay. We know there are known bottlenecks, and we are working on it. And this is first performance.
Cisco and those guys.
Oh.
So one question about implementation. So basically, it's a semantic difference.
Yes.
You implement it.
Yes.
Like do you reduce the number of copies from the past, and you use different way to do notification using tokens. Basically, what do you think the game will come from?
Okay, so game essentially comes from, so on the PX side, we are doing send page. So this is kind of a zero copy mechanism. And application only does a single asynchronous post and application returns. You don't need any more application scheduling to actually actively send the data from the user buffer. There is a kernel thread which is going on behalf of the application. On the receiving side, it's the same thing. So we have a hook, we register our function in the soft IRQ processing of the networking stack, and we get an up call whenever there is a data. And in the up call, we figure out what pages are involved, and we do immediately copy the data in the same soft IRQ processing, and we just finish the whole network processing on the RX file.
So in theory, there should be some enormous gain.
Yes, but the gains also, this thing is bounded by the networking performance. So we cannot show the gains in terms of the latency and bandwidth, because the only gain is like to fill up the pipe of 10 gig. If 10 gig is small enough, then only thing that we can show is the better CPU usage that we have. So if you have like 20 gig or 40 gig Ethernet, then those CPU, the things will become a CPU bound, and we'll have a better performance than the normal TCP stack.
Need some experiment.
We are actually setting up faster Ethernet cluster in our system.
Okay, thanks.